We're live, day 5 of learning linear algebra entirely with ChatGPT. I think I'm getting more of the technical stuff down with OBS and all that, whoops, as I go and show my desktop. I'm going to just pull up the doc because I realize sometimes I forget to title the stream properly. Stream information, make that a new thing. Yeah, I did not title it correctly. That's all right, though. Let's see if I call it now. Day 5 of 30. Update all titles. So before I begin today, I want to try something. If you tuned in last night, you will have noticed that I did some coding. I thought it would take 17 minutes. I thought I could really quickly make a Chrome extension that would be helpful for this course that I'm taking, / anyone trying to learn stuff on their computer online. But it took a bit longer. It took 64 minutes in all, a little over an hour. I ran into a couple little bugs. I found Gemini 2.5 Pro to be not very helpful for coding, did not deliver on the hype. Went back to Claude 3.7 / just using Cursor and its automatically selected model. It's a very cool thing if you don't know, by the way. Cursor, which is what all the software development world is obsessed with. It's a new code editor. It's a place where you type your code, but it has what's called an agent that does the AI stuff for you. Oh, thank you. Had some breakfast here too. I'm going to try to consistently do these at 8:30 a.m. You might hear babies screaming and robo vacuums rolling and dogs barking, but that's all part of the experience, isn't it? Moving my mic a little closer to me and away from the chaos. So as I was saying, Cursor is this really neat tool that you can use that will integrate AI into your code editor so that you can very easily just type real world prompts and it'll make the code. A couple inspections, I had to just manually change a couple things to get it to work, but it works. And I'll show you right now how it works. So if I go here, I'm going to use this app. It's called Diffuse, and I will go to lesson 4, which I'm trying to do right now. Actually, wait. You know what's weird is lesson 4 was not what I did yesterday. They were giving me different stuff than what I asked for, but let's just see this matrix. All right, I'm going to go ahead and just copy this. Give me the lesson for this. All right, this is something that's classic. I don't know what this means. So I can either click up here to go take a screenshot, or I'm going to use Command-Shift-S, which is the keyboard command. And then I go get this summary right here. Boom, screenshot saved. Now if I open a new tab, look at that. I see this thing that I screenshotted. Now, I don't know why it's actually kind of dark shaded. It's a little annoying. But I can get an AI explanation of this. What does null space look like? If it's just the origin, it's a unique solution. If it's a line through 0, that's one free variable. So this is like a 3 for me on the confidence scale. If I get the AI explanation, let's see if this still works. I only tested it one time at the end of my stream last night. So it explains it, but it doesn't give it a real explanation of what the concept means. So I'm going to have to edit that a bit, but you see it's a starting point at least for being able to have my notes come. And this happens every time I open a new tab. It'll show this or whatever other saved screenshots I have. So anyways, I'm going to make use of that here. Let's start going through this lesson though. So the core concepts: matrix, vector, multiplication. So given that we have a matrix such that it's in an m by n real space, m by n dimensions, and that the vector is n dimensions. So again, these columns are vectors is one of the key things. You know what? Also, I want to highlight a comment that I got that I'm actually going to screenshot here on YouTube. This comment said, I liked this comment a lot. My linear algebra professor started every class with the call and response, "What is the definition of a basis?" And we would respond, "A linearly independent spanning set." This is the classic thing. So here, I'm going to get that. Oh, I did the normal screenshot. See, it's a bad habit. So Command-Shift-S. Boom. So now if I open a new tab, sometimes it'll show this, sometimes it'll show the other one. So I go 4. And I'll update this over time, and it's going to give me more frequently things that I have low confidence on to review rather than high confidence. So let's go ahead and keep rolling with this lesson. So a x vector is a linear combination of the columns of A using the vector as weights. So if A is 1, 2, 3, 4, and the x vector is 5, 6, I do 5 times the first column plus 6 times the second column. Okay, cool. I've actually done this sort of matrix multiplication before. You go, I just kind of memorized it, the method, but you roll down the, you go down the column and across on the thing that you're multiplying by. I didn't explain that very eloquently, but let's go and do some practice. Then we have matrix times matrix multiplication. I want to see how this is different. But I know that you need to have the same inner dimensions. Notice it's an m by n dimensional space versus an n by p dimensional space. You need the inner dimensions to match. That's important. So matrix by matrix example, 1, 0, 2, 3, 4, 5, 6, 7. I do 1 times 4 plus 0 times 6. Notice I go across here, down here. And I do that for each of these. For the top left, I go the top row and the first column. For the top right of this answer here, I go the top row 1 times 5, 0 times 7, I get 5. And you go ahead and do all that. Another thing, matrix multiplication, because you're going rows in one of them and columns in the other, it's not commutative, meaning you can't flip the order of it. A times B is not the same as B times A. It is, however, associative. That's interesting. I need to think about that, why if I multiply a matrix times 2 matrices, it's going to equal to that. So that's interesting, and why it's distributed. So interesting. And then we have the identity matrix. It has one diagonal, one's in the diagonal and zeros elsewhere. Again, familiar with that. Then I have the inverse matrix here. The inverse matrix says is what I multiply matrix by to get it equal to the identity matrix. So here's an example of the inverse. I have 1, 2, 3, 4. So there's this formula that I'm going to screenshot here. It's kind of better than taking notes in a lot of ways, just to quickly screen grab things that I want to review. Okay. So it's interesting, they don't explain a lot of things here. They're skipping a lot, this ChatGPT. But the determinant is AD minus BC. I know that. And they don't clarify what A, B, C, D are, but it would be A, B, C, D. So to find the determinant, I go 1 times 4 minus 2 times 3. All right, so I got some practice problems. So far, this appears to be an easier lesson than the last couple. Now, it's just sort of stuff you do learn in Algebra 2. So I have to multiply these matrices. Excuse me for eating a little bit. I'm just going to overview this and then go in. Problem 2. I need to find the inverse. And problem 3, I need to multiply a matrix by a vector. Cool. And then the final concept quiz. I need to find the size of what they're going to multiply, which I think will be 3 by 4, and ask if I can compute BA. The answer is no for that, because the inner dimensions of BA would be 2 by 4 and 3 by 2. the 4 and 3 don't match up. They need to match up. So, man, eating over easy eggs on toast is a difficult thing on a stream. Very messy. So, asked, what is the effect of multiplying a vector by the identity matrix? Well, they didn't explain that at all. Again, I'm seeing the shortcomings of using ChatGPT only to teach you linear algebra. They asked questions that they just clearly didn't explain, but the effect of multiplying a vector by the identity matrix, I assume, is that the vector remains unchanged. That's sort of the point of the identity matrix, is that it's like 1. Okay. I don't know how to answer Q4 just off the top of my head. So let's go check this out. I'll do the practice problems now. All right, moving my practice plate over. All right. So multiply the matrices. All right, 1. I assume they want just AB. Do they also want BA? I don't know. I'll just do AB. 1, 2, 3, 4 times 0, 1, 1, 0. So to do this multiplication, I want to have it equal. It's going to be a 2 by 2 matrix. I go 1 times 0, which is 0, plus 2 times 1, which is 2. I go across on this one and down on this one. Then I'll get this spot here in the top right. For the top right spot, I go 1 times 1, 2 times 0, which is 1. I think we're going to get some sort of slightly inverted version of this, just the numbers in different locations. Let's go to the bottom right. Now I go 3 times 0, 4 times 1, 4. And then finally for the bottom right, that was the bottom left. The bottom right, I do 1 times 3, 4 times 0, plus 4 times 0, which is 3. All right, so that's the answer to problem 1. I'll say and problem 2 here, I want to find the inverse of A. So I go 1 over determinant of A. Let me make sure I get the whole formula. Times A was 2314, so this is going to be 2 in the bottom right. Wait, yeah, 2 in the bottom right, 4 in the top. I switch those 2 spots. And then I keep negative B and negative C. But I want to make those negative, so it becomes -3, -1. Let's see if this is right. So 1 over the determinant, I can find the determinant of A, which is going to be AD minus BC. So 2 times 4, so 2 times 4 minus 3 times 1. And then just writing dot, dot, dot. It's the same as it was above. So this is going to be 1/5 times this whole thing. So it's going to be 4/5, -1/5, -3/5, 2/5. All right. I think there's another way to find inverses of matrices, but I'm not sure exactly. So explain the different ways to find the inverse of a 2 by 2 matrix, as well as an example of a matrix without an inverse. If the determinant's 0, that's one way to make sure it doesn't have an inverse, because you'd have 1 over 0. Maybe that's the only way. But let's see. We have problem 3 now. So problem 3 says that A is 1, 0, 2, 1, and x vector is 3, 5. I'm essentially just multiplying these. So I don't know why I wrote over 5. Okay, so in order to solve this, here, I'm going to pause the stream for 1 second to wash my hands. I got some gooey egg on it still from that breakfast, which is delicious, but pause. All right, we're back. Hands clean, eyes clear, heart pure. Let's go. So, do I have the chat open anywhere, by the way, in OBS? No, I should open that. In the off chance that somebody tells me, oh, your audio is not working, or something like that. Chat, docs, chat. Oh yeah, I got the chat. So I'm fiddling with OBS stuff here. This is an easier. There we go. Easier lesson than some of the others. So anyways, the answer is going to be 1 by 2, or a 2 by 1 matrix. So 1 times 3 is 3, 0 times 5 is that, so 3, 2 times 3 is 6, 1 times 5, so 11. This is the answer for x vector, a x vector. All right, and let's go and see this. So the final answer to the first one, 2143, nice, I got it right. So I can use the inverse formula where I switch these and make these negative. The thing is, I don't like that because I don't understand why. But I did get the right answer, 4/5, negative 3/5, negative 1/5, 2/5. And multiply matrix by a vector, 311. Okay, I got all those right. Those were easy, relatively. Explain the different ways to find a 2 by 2 matrix. Okay, good. That's a good question. Meanwhile, I'm going to start the concept quiz. And then I think after this, I'm going to go to Grok and ask Grok for this lesson. Grok, maybe the most underrated of all of the AI large language models you can use. So Q1 is asking, if A is 3 by 2 and B is 2 by 4, the size of AB, I believe is going to be 3 by 4. No, those are the two things. Okay, Q2. True or false? If AB equals AC, then B equals C. Ooh, interesting. I think that's true, but I'm going to screenshot this one because I'm not 100%. What is the effect of multiplying a vector by the identity matrix? Multiplying a vector by the identity matrix does not change it. Explain what the inverse vector matrix does to a vector. Why is it like dividing by matrix? So I need to understand all these things. So first, the formula method, quick and exact. I find the determinant. Yeah, AD minus BC does not equal 0 means that the inverse exists. Cool. Matrix is not so it's if the determinant is 0. And columns, its columns are linearly dependent. It doesn't have full rank. So if its columns are linearly dependent, that means its determinant is 0. Matrix collapse space. It squashes the two-dimensional plane into a line so it can't be undone with an inverse. That's crazy. Screenshotting this whole thing here. All right, we got this summary table, fast and exact for any 2x2 matrix. Okay. Cool. Answer the concept quiz. All right, we'll go for the concept quiz problems. Meanwhile, I'm going to go back up. Way up. I'm going to actually copy all of these. To teach me linear algebra, elite college level, MIT, upper Ivy, etc. I'm on lesson 5. Give me a lesson plan. Here are the first 5 lessons. See if it recognizes that. I like to understand what the determinant means a bit too, because I understand that it's useful for the formula, but what does it actually mean? So AB is 3/4, BA is not defined. I was right for the first question. This is false. I had a feeling. This is a classic non-cancellation trap. Matrix multiplication is not cancellative. That is that AB equals AC. This is especially true if A is not invertible. All right. I'm going to screenshot that for sure because that's a tricky one that I got incorrect. Oh, I have an example too. Whoops. I'll undo that. So if A is a 0 matrix. Oh, okay. Classic. A is a 0 matrix, then B and C can be whatever. Okay. I don't actually need to screenshot that. I guess I should always consider the 0 example. It's a classic thing in basically any math class. Think about 0, think about 1, think about -1. Those are the most interesting numbers to plug into anything to see if something's always, sometimes, or never true. What is the effect of multiplying a vector by the identity matrix? It leaves vectors unchanged. It's the do nothing. So yeah, it's like the number 1. This is what I thought. So if A is an invertible matrix and B is the vector x times A, then applying the inverse of A undoes the action of A. Okay. It undoes the transformation applied to A. All right. What is the determinant? Why is it useful? And also explain why we combine matrices and vectors and why that's useful. So that's an interesting thing there. So let's start looking at this. Grok Warm up and recap. X is a column vector in R squared. How might we combine A and X to get B? Just going to scroll through all this. So I can compute that. That's what I've been doing. I could find AB and BA. So three-dimensional identity. Practice, keep mastery. Oh, okay. Lesson 6 is where I get into the other way of finding the inverse. I knew there was another way. Why doesn't AB equals BA relate to the geometry of linear systems? That's nice. I like that they give me the challenge. So identity matrix is just means multiplying by 1. All right. This whole matrix vector thing is still a little confusing to me for matrix vector product and all that. X is a column vector in R squared. How might we combine A and X to get B? So this is also a quick lesson that Grok gives me. It's not super in-depth, but let's go ahead and look at this answer. So yeah, I get that that's it. The determinant measures the scaling factor of area, volume, or hypervolume when applying the linear transformation of A. Okay, it's the scaling factor. Whether the transformation preserves orientation or flips it is based on the sign of the determinant. Okay, so you have a vector going in some direction. The vector is basically the multiplier, the scaling factor for that. Whether the matrix is invertible, the determinant of A, yeah, I know that. So it's not, you can't find the inverse of a matrix if the determinant is 0. Why? There's the formula, but if the determinant is 0, A is singular. It's not invertible. I'm sort of getting this. Like, that's why we have 1 over determinant in that formula, because it's the inverse of the determinant that you use. If you multiply something, if the scaling factor is 3, meaning we make a vector 3 times as long in the same direction, then you want to multiply by 1/3 to get back to the original. That's why we go 1 over the determinant, 1 over the scaling factor, or the multiplier. I get that. The other stuff's a little bit wonky still, but yeah, the geometric examples are good for me to visualize it, like to have a geometric visual understanding. So this doubles the x direction and triples the y direction. That makes sense to me. So the area gets scaled by 6. So the determinant is that. I see. Maybe part of my issue is I'm thinking of vectors as one-dimensional lines, and vectors can be two-dimensional planes too. Okay. Yeah, Kramer's rule is something I'm familiar with that we'll get into, I'm sure. So matrices allow me to stretch, rotate, reflect, project, flatten, and compose systems. This model is a real-world system. So in computer graphics, every 3D object is represented by vectors, and transformations are matrices. Wow. You're solving a system of equations. Combine all equations into one matrix and multiply it by a vector x. You're in machine learning. You have data. You have a matrix of inputs, and the weights are vectors. So I understand that, I think. And the predictions will be the matrix times the vectors. Wow, that's crazy. And then in physics, forces, rotations, change in coordinate system, matrix vector multiplication. So matrix vector multiplication, I think I understand it now. Matrix vector multiplication is a way of compressing and solving entire systems at once. That seems like a good thing to bullet point. And you'll see I can view all these screenshots here. I don't even know why I got that. For example, this system, that's awkward. Becomes this. So solving a system of equations becomes one elegant matrix equation. And it works for any size of system with any number of variables, any kind of transformation. This is cool. I'm kind of seeing how linear algebra connects to all the other math stuff. I get it with system of equations. Now I see this is a good way of explaining why it's useful, because I was thinking, oh, it's just easier to use algebra to solve a system of equations. But now I'm thinking, okay, this vector matrix multiplication is kind of cool. And I get that xy is a vector now because it's a vertical column. Is that right? I hope so. A visual walkthrough of a determinant or transformation to build your intuition with hands-on. Yeah, I'm going to ask for both of these. Yes. And you'll notice Grok was nice. I'm going to actually do that 1 3x3 Grok problem. I'll do that while this is loading, but it's sort of also the 80-20 rule with these AI models. Like I get 80% of what I'm trying to learn from one of them, and by trying to find the right model to get everything perfect, I'm sort of putting in more effort than is worth it. Sorry for the loud noise. Robo Vacuum is unloading here. So, as I said, chaos in the mornings, but I'm going to try to stream more regularly around this time, 8:30 a.m. Pacific. I think it's a time I can consistently hop on my computer for an hour before the day takes its toll on me. So let's look at this. Where's that 3x3 matrix? I wanted to do the inverse of that 3x3. Yeah, verify. All right, so I'm going to go to this one. The inverse of 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll just screenshot this. Explain this. So the columns of the matrix are two vectors. And these form a parallelogram in R2. Interesting. I'm thinking of this as the x and the y. The area of that parallelogram is AD minus BC. Okay, this is definitely worth screenshotting. If the determinant is 1, the area is preserved. Determinant is 2, the area doubles. Okay. I think I'm kind of understanding this. This matrix collapses space onto a line. Yeah, no area, no volume, no inverse. Okay, I actually get this, I think. Oh, this is getting crazy. Visualize a matrix system machine. So first off, all this is saying is that the identity times this is equal to that. So I could find the matrix product, which is annoying. I guess I should ask it for a 3x3 matrix multiplication problem, or I can just look at this one. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Need some harder problems from this lesson. Would be in an MIT linear algebra class. I think it's always good to ask that because, again, the standard that it gives is just very basic. And that's true of all AI. You never want to just rely on it as your sole source of truth without any further interrogating. So to find the matrix product, let's see. Column 1 of A, 1, 4, 7. I go 1 times 1, 0 times 4, 0 times 7. Oh, but 3x3 matrix multiplication is easy, actually. Sorry, I was thinking of finding the inverse with the determinant, which I guess is going to be next lesson. So that's fine. Oh, what? This is not right. Basis and dimension. Maybe I should review that in a little bit if I have some time. So, construct matrices with desired properties. Construct two different 2x2 non-zero matrices, A and B, such that, all right, AB equals 0, but A does not equal 0 and B does not equal 0. Nice. Okay, these are the kinds of good problems I like. Matrix equation puzzler. A, B, and C are square matrices such that AB equals AC and A is invertible. Proof that B equals C. Okay, a proof. I'm going to low-key screenshot a bunch of these. All right. If A is invertible, so how many problems are there? 6. Explain problems 1 through 3. I'll just start with that. Construct matrices with desired properties. Two different 2x2 non-zero matrices such that AB equals 0, but A does not equal 0 and B does not equal 0. Okay. So I guess I can set up a system like this. That's one way to approach problem number 2. And here I get that A equals 1 times A plus 0 times C equals 0. Is everything going to be 0? I hope not. B. 1 times B plus 0 times D. Yeah, B. I thought there'd be a way to make it work. Maybe 1001 was not the way to do it. Problem 3 is easy. Most matrices won't be invertible like that, won't be commutative. Determinant of A is 6 minus 6. It's not invertible. So now geometrically, what this matrix does to space, it collapses 2D space on itself. I get this. That's starting to make sense. Inverse via augmented matrix. I will screenshot that. There's a chance I forget it. again, I'd rather be liberal with my screenshots and notes rather than leave something that I sort of get at the time, but then forget. We always overrate our memory, basically. So I'd rather be safe than sorry. And so inverse via augmented matrix here. Use the inverse, find the inverse using row operations on the augmented matrix. Oh, this is what I remember. Gauss-Jordan, yeah, this is the easier way to find the matrix. Not the easier, in my opinion, the better. So first I want to see if I can, let's see what they do for problem 2. I don't want to waste time. You multiply both by the inverse. Ah, the associative property. Yeah, okay, that makes sense. It's worth screenshotting. If A is not invertible, it doesn't work because you can't do that step. Yeah. Non-zero matrices, 1, 1, 2, 2. Yeah, that was my issues. I got zeros. 1, 1, 2, 2. Yeah, I figured there'd be some numbers there. So this is weird because it's just guess and check. Ah, this works because the column space of B lies inside the null space of A. Whoops. I like to be able to highlight things there. All right. Well, anyways, yep, any whole thing works. Now 4 through 6. We're coming up to the full hour here, guys. This is cool. I'm gonna go and pull up the chat again just in case somebody said something. Nope. That's cool though. So I'm curious how they set this up. Meanwhile, go back to the grok. One thing I'll say about grok is it has a big advantage for any current events, anything where you feel like there's a lot of knowledge on X in particular. So I would use it for like best practices on new coding technology, like a new AI model or a new update of cursor, because it can pull from that data uniquely. Also, it has the advantage of probably being promoted by X. If you're trying to get promotion and followers on X, you're much better off using Grok to do stuff than ChatGPT. In that case, maybe it was a miscalculation by me to use ChatGPT to teach me linear algebra rather than Grok. But, you know, much lower probability of Elon ever retweeting it, for instance. But I think that ChatGPT is the more well-known model at this point. But maybe I'll switch to Grok at some point, or maybe the next thing that I learn after linear algebra in 25 more days, 24 more days, will be something entirely through Grok. So let's look at this here. Maybe some harder problems from this section. So if you want to reverse the order of operations, this is function composition and disguise. Think of matrices as functions. That's cool. So matrices are like functions, which I sort of understood. There are ways that you can manipulate a vector in terms of its angle, direction, or magnitude. So to undo AB, you must undo A after you undo B. Yeah, function composition. Inverse of B, inverse of A, AB. So the first direction. I don't love this proof. Flatten into 1D subspace. I was right. Cool. Find this using row operations. This is what I wanted to do. So I'm going to write this one out. 1, 2, 3, 5. I've noticed sometimes for these challenge problems, it just goes straight up to the next lesson, which is actually good. It's nice to preview a lesson before you learn it. Even if you're not understanding what's going on, you at least prime your brain for some of the stuff, and then it's more likely to click because it's not technically the first time you're seeing it when you're in the lesson. So I like that. And I like in general that I'm in this sweet spot of desirable discomfort with learning where I'm really scrambling at all times, but I feel good afterwards. I'm having stuff click. I'm not totally lost. And most importantly, I'm just trying to ask good questions as we go through this. And that's the best way to use AI, is to ask good questions, of course. So I'll make this augmented matrix here. Make this augmented. So it's 1, 0, 0, 1. I put the identity matrix there. And then I have to eliminate the pivot below column 1. So I would go R2 is R2 minus 3 R1, I presume. Yeah, okay, that's what they're doing as well. So then R2 becomes 0. 5 minus 6 is negative 1. 0 minus that is negative 3. And 1. All right. And then I need to make the pivot in row 2 a 1. So I need to get this to be reduced row echelon form. So I multiply it all by negative 1, so it becomes positive, positive, negative. And so the new matrix is going to be I need to do something to the first row too. I need to eliminate above the pivot in column 2. Yeah, so to do that, well, first I'll write this new matrix right here. 1, 2, whoops. 1, 2, 1, 0. And 0, positive 1, positive 3, negative 1. And so then this top row, I want to go R1 is going to be R2. Sorry, is R1 minus 2 R2. So we'll get rid of this 2 right here. So that's going to give me a new matrix that looks like 1, 0, 0, 1. And then 1 minus 2 times 3 is negative 5. 0 minus 2 times negative 1 is 2. And so I assume this is the inverse. Negative 5, 2, 3, 1. This will probably get a lot faster for me. Nice. All right. That was great. Let's see what Grok says for some harder problems. Compute AB and BA. Verify that AB does not equal BA. Compute AB to the T and compare it. All right, that's tricky. They gave me a lot of harder problems. Oh, they gave me this. Okay. So I have no idea how they figure out AB to the T here. This stays 2, then this comes 1 on 1, this comes 5 1 2. So just for example, I'll see what this negative 2 is if I multiply this by itself. So if I multiply this by itself, it becomes 2 times 1 plus 1 times 1 plus 5 times 1. Yeah, I don't know. What does this to the t mean even? It's a little overly verbose grok, I'd say. The transpose of a matrix swaps its rows and columns. If C is a matrix, then the entry C to the T ij equals Cji. What the heck? This is the transpose of a matrix. Okay, that's what that means. It's not an exponent thing. I was trying to do it like squared or something. So the transpose just means, yeah, you switch it so that the 1, 1, 1 is now here. Okay, AB transposed, B to the T. B transposed times A transposed is going to be the same. Cool. The transpose of a product. I'm going to get all of this in a screenshot. That's interesting. Okay. Identify matrix and scalar multiplication. 3 times the identity matrix, A minus A. A squared and A cubed. A to the N is going to be that. Compute A. Dang, these are crazy. One minus 0. This does have an inverse. Oh, wait. A matrix has an inverse only if the solution to AX equals 0 is the trivial solution X equals 0. Oh, yeah. Can we also just see if the determinant's equal to 0? The determinant is AD minus BC. It is invertible, yeah. Okay. So this is another way of doing this. Wow, this is just a lot of messy matrix multiplication. Glad I don't have to do that. All right, matrix times X vector equals B. All right. Feeling positive about this overall lesson. Success. Not too hard. I'm going to take a quick peek at what lesson 6 is going to be. And linear transformations and current. Wait, what? Oh, it's unit 2. Did I skip to unit 2 for one of these? I hope not. I probably did skip to lesson 2 for some of these. Haha, that's funny. All right, well, this is... No, this seems right. This is what I've been doing. Invertible matrices and Gaussian elimination. All right, I'm gonna save that so it's ready to go. I call this the Ernest Hemingway method of when you're finishing something, get started so you can jump right back into it. It's often easy to forget where you stopped. Hemingway would often stop writing mid-sentence even, so that when he picked up the next day or the next writing session, he would be able to immediately get into a nice little stride with it, rather than having to gather up all the energy, fight against the inertia, establish a momentum again. So let me just see here. I got lesson 6. Then we got a checkpoint and a major test coming up. So before that major test, I probably will want to review all my notes, screenshot the important stuff, review that, and then I'll take the test. That might be a slightly longer lesson. I'm trying to stick to an hour a day. I'm trying to stick to not having devoted homework time, more just learning stuff passively through my extension Diffuse that I made, Diffuse AI. I might do another stream later today. It was fun building that last night, and there are a lot of little things that I know I want to fix, like having it not shade dark the thing that I'm screenshotting, and get the AI explanation to be a little bit more fine-tuned so that it knows what I'm learning. I can just hard code in linear algebra for now, but ideally make it for anything. And some other little things too, like making it show the whole image here so you can easily see what you're dealing with, sort by rating, etc. So anyways, that's it for today. Thanks for tuning in. I'll record a quick little short as usual to talk about takeaways from today. And I'll see you guys tomorrow. Plan on 8:30 a.m. It's usually a good time. All right. Peace out.